Hello, class. In fact, I think I'm going to switch over for a second just to record me for posterity. Here I am. I'm going to do the next lecture in the series for the Network Theory 1 course. And this is, excuse me, on first order RC and RL circuits. Let me just get back to the page. We've had light streaming in here. I've sort of covered that up. I hope that everything's okay for the lecture. We'll see how it goes. This is the first lecture I've done since I did like 100 lectures a month ago. I think it was like a month ago that I finished those. So what I want to do is I want to look at first order source-free RC circuit. In fact, I'm going to follow very much along with what your book has. Now, when we look at a source-free circuit, we're looking at the node, and of course the node includes all of that top section. I've got a resistor here, and I've got a capacitor. We've left some type of positive voltage up here. We don't know what that is because we've just removed the source. And we don't know if the capacitor is entirely charged or if it's partially charged or what. I don't know why I pulled that out of there. I should have. Oh well, I'll just get it. No, there we go. Just don't want the thing moving around too much. There. Okay. Now, so we've got a voltage up there, and down here we have ground. So if we've got a ground and we've got up there, irrespective of which of the two different types of components we have, passive components we have here, we've got a positive voltage on this side and we've got a negative voltage on this side. Now, if this was totally uncharged, the current would obviously be flowing out of this positive source and down into the capacitor to continue filling the capacitor. I mean, that's why we call it a capacitor, right? So I sub C. And also from the positive to the negative, that's the direction that current is flowing here too. So this would be I sub R. And so if I wanted to look at the node, Kirchhoff's voltage law, oh, I'm a little tangled here. Wow, I am going to definitely spill that tea. Let's put that over here. Trying to get the studio back together. Excuse me for a little organization here. So if we've got those flowing out of there and we do a summation on this node that we have up at the top, let me get my other colored pens too, right? So we have a node, oops, right up here. And I'm going to say that both of those are flowing out of there, and of course you know that that's not true, and I'm going to show you that in an example later on. But for us to look at the loss of energy that we've got, we're going to set it up so that and it doesn't matter. We don't know if that's entirely filled or if it's not, but we know that we've got a positive voltage up there and a negative voltage down here, and we know that that node then has to equal 0. Now we may have one of those in the wrong direction, who knows? But what we can do with that is we can say, okay, what is I sub C? We go back, and this would be in our previous lecture, and we know that I sub C equals C dV dt, right? And we know that I sub R is just going to be, V equals IR. V equals IR, so I has to be V over R, doesn't it? Right? So I sub R and I sub C, and we can just replace them. So I've got C dV dt plus V over R equals 0. Let me get another pen that's got a little better ink in it. And I can rearrange that a little bit too. Let's divide both sides by C. So I get dv, oh, that's much darker, dt plus v over rc equals 0, right? Okay. Now, how about we take this one over to the other side? So if dv dt equals minus v over rc, right? Now, let's switch these around. So I've got dv over v. That the v's, by the way, are all voltage. I should probably make those a little bit larger, but they're all voltage. dv over v, and we know what the integral of that would be, and that equals minus 1 over rc dt, right? I think everybody can see that. Boy, I'm going to have to move my chair over or something. I don't know. Well, actually, it's coming up pretty good on the page there. That's good. I want to talk about, of course, when we do integrate this. If we integrate this with respect to v, so let's do that. So let's integrate this with respect to v, and I'm going to integrate this with respect to t. Now, this is just a constant, right? So I can take that outside of the integral. And 1 over v dv, we know that that is just the natural log of v, right? So we've got the natural log of v on one side, and we've got minus t over rc on the other side, right? I think everybody can see that. Plus, we want to put some type of constant there, right? So I could say that this is just a, and then, but I'm going to say that this is the natural log of a, right? It's just a constant, right? This really is just equal to C1 or A1 or whatever, but we're going to say that it's the natural log of a, whatever that is. It's just a constant. So what we would do is we would take the exponent of the constant. Anyway, I think everybody gets the idea. So now basically what we do is we use the natural log identity function. So I've got the ln v minus ln a equals minus t over rc, right? And this would just be the natural log of v over a, because we use the identity that the natural log of a times b equals the natural log of a plus the natural log of b, right? That's one of our identities, not natural log or exponential identities, right? So logarithmic identities, whatever you want to call them. And we know that the natural log of a divided by b is just the natural log of a minus the natural log of b. And of course, that's what we're using right here to get the natural log of v over a is going to equal minus t over rc, right? So what we can say then is we can say that v over a is going to be equal to e to the minus t over rc, right? Everybody, because of course the inverse function of natural log is exponential, right? And we know that the natural log of e to the a equals e to the natural log of a, right? Because they're inverse functions of one another. Also the natural log of x to the n equals n times the natural log of x, right? Does everybody see that? And There's one other one too. What is it? The log. Well, that's a log thing. I think I already taught that to you, but you'll see it again in communications too. But anyway, well, maybe not. All right, log. Let's say to the base 2. It doesn't matter which base. Could be the base n of x equals log to the base 10 of x times log to the base 2 of 10. I'm just using an example. You can, switch between any logs there. Log to the base 2, log to the base 8. That is a 2. All right, so that's just an example of that. Yeah, if that light's just still trying to creep in. I've got a little thing over the curtain over there to keep it out, but it's trying to creep in. All right, so anyway, we're down to here, and we see that we've got V over A, but we know that V at t equals 0 equals V0, right? So if I was to make t equal to 0, that makes E equal to 0, and E equal to 0 equals 1, and so that means that V equals A, or A equals V at time equals 0, which is V0. So in the end, what we get is we get that the voltage at any time, voltage as a function of time, the voltage decay as a function of time, is going to be the original voltage that we had up there, V sub 0, times E to the minus T over RC. Now I want to circle that, right, and put a star next to that. Let's put a couple stars because it's so important, right? And so we really look at that as minus T over RC. Now, what we call RC is we call RC, in this case, with capacitor in series with a resistor, we call RC the time constant. And let's look at that equation, by the way. V of t equals V0 e to the minus t over RC. Let's look at a general, equation for e to the minus x, right? That's what I want to look at, because that's what we've really got there, isn't it? When we're looking at this equation, you can see that I've got minus t over RC, and RC is the time constant. So if I have minus t over, if t equals RC, right? If t equals RC, then V of t is equal to the original voltage times E to the minus 1, right? Because T and RC are equal, so just be the same as RC over RC, or T over T, and it would be to the minus 1. How about if T is twice as great, right? So if T equals 2 RC, then V of T equals V0 e to the minus 2, right? Does everybody see that? See what I'm saying here? So really what we want to do is we want to look at the function of e to the minus whatever, dependent upon x. And x, of course, is just, in other words, what we're going to be looking at is x, 1, 2, 3, 4. Let's just say that this is 1, 2, 3, 4, 5, 6, 7, right? So this is x, And we're going to look at, and of course, this over here is y. And what is y, right? Y right now, y equals e to the minus x. That's all we're looking at here because this is exactly the same equation as y equals e to the minus x. Well, let's look at that and see where that is going to put us just generally, just as a percentage. In fact, let's say that I have, well, we want to start at 0, don't we? Time is equal to 0. Well, if time equals 0, then it would be e to the 0. E to the 0. Anything to the 0 is 1, isn't it? So if I have 1 times v sub 0, that would make this v sub 0. In fact, why don't we, we could call this y, but we could really even just look at this equation and see how this were to change. But let's look at this generally. Okay. I'll tell you what, I'll make it v. And we'll call this point up here v0. That's where it starts. And now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, no, we're calling this v0 up here. Sorry about that, because that gives me 10, and that makes it just so much easier. And so when I come down to 1 here, I want to be at 37. So 1, 2, 3, 7, right? So I'm coming down from here. Oh, let's plot another point. So, okay, so I want 13.5 right about there. And at 3, it is 5%, so right about there. At 4, it's 2%. And at 5, it is 0.6 of a percent. Right, so here's how it looks. This is how the function looks on a graph. Isn't that great? So we start at v0 at 0, and then by 1, we are down to 0.368 v sub 0. After 2 time constants, right, so this is 1 time constant, so this is tau. This would be 2 tau. This is what t equals 2, and tau, of course, like I said, is RC. And then 3 tau, 4 tau. So the second one, we're at 0.368 or 36.8%. The third one is at 13.5% or 0.135 times v sub 0. After 3 time constants, we're going to be at 0.05 v0. And at 4 time constants, we're going to be at 0.018 v sub 0. At 5, I'm just going to give you this. I'll just put it down. Well, I don't know. I suppose I'll just put an arrow over here because I'm running out of room. At 5, we're down to 0.0067 v sub 0. All right, does everybody see that? So that's how I discharge. That's what the discharge of a capacitor looks like. Now, what does the charging of a capacitor look like? Now, we've done all the discharging over here, and we figured out that, yes, it follows the e to the minus x thing, right? But what does the charging of that look like? And I'm going to draw this down here. I'll try not to, I want to look at a couple things. First, the charging over, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sure, we got plenty enough there. So this is v sub 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right here. And I'm just going to make a little line across here. We're going to do the same thing as we did before. 0, 1, 2, 3, 4, 5, 6, 7, 8. The reason I put 7 and 8 on here is really just to show you that it could go on forever, right? But I mean, it's diminishing returns, isn't it? So, you don't want to. Now, the charging of a capacitor. The charging of a capacitor, as you would assume, is sort of just the reverse of the discharging of the capacitor. And I want to go up the same way. It's basically this curve here inverted. So when we start to charge a capacitor, and really what am I looking at as far as the V0, right? This is really saying that once I have that voltage source out of here, the voltage on the capacitor, the voltage in that system is going to, the voltage up top here is going to leak out like this. It's going to leak out of the capacitor through the resistor to ground. That's what it's really saying. Now, when I'm charging a capacitor, and I want to draw another little circuit here too, that is a circuit that can really do both of the two things that we're looking at. Let's say that I have a power supply, and I've got that power supply connected to ground, right? And I also have a little switch on that power supply. So the switch could be hitched up to number 1, or the switch could be hitched up to number 2, right? So it's a swinging switch. I'll just draw the switch here, right? There's my switch. It can go to 1, it can go to 2, but then that is connected to a resistor in series with a capacitor, right? So I've got a resistor, I've got a capacitor. I can switch between these two. Now, I want to put this, I should have put that a little bit further over, but I'll just draw it like this. That second thing right there is connected to ground, right? We're connected. So if this swings over here, then the charged capacitor is going to discharge through the resistor to ground, right? So we've really got two pathways there. We've got a pathway for the charging, right? Because for the charging, we would just have this, right, through here, through there, and that would charge the capacitor, right? And of course, the capacitor, the other side of the capacitor would send electrons up to this. So, actually, yeah. Now, we've got another pathway too. We've got the discharge pathway, don't we? And the discharge pathway is going to be from the capacitor then up through here, down through this to ground, right? Does everybody see that? So that's what's going to happen with the discharge. And we're going to look at that and look at the current and everything else inside that circuit. So when I'm charging a capacitor, the voltage on the capacitor starts at 0, right? There's nothing there. But as I start to run current through the capacitor, actually I'm not running it through the capacitor, but I'm running it onto this plate, and that's pushing the other electrons. So remember, a capacitor starts as a short. Let's write that because it's so important. Capacitor starts as a short circuit and goes to an open circuit, right? So when we first look at the voltage that is across the capacitor, it's really 0, right? When when it's fully charged. And what have I? Oh wait, the voltage across is a maximum when it's fully charged, and then when I discharge it, of course, it's going to have nothing across it, like I've got here. This is my discharge mode, so that would be the orange one. I would be discharging through here. So this would be the orange discharge. Well, I'm losing my orange. There's no. So that's the orange discharge. I guess I'm going to have to go. I've got a whole bunch of new ones, though, so we'll try those out, too. And then the charging of the capacitor. The voltage I've got here, of course, is across the resistor is just going to be the voltage drop across the resistor. But as I charge the capacitor, the voltage on the capacitor is going to start at 0, but then after 5, approximately 5, but let's just do this the opposite. So what I would do is take the 36.8% off 100%, and that would give me 63.2%. So 1, 2, 3, 4, 5, 63.2%. Let me just write that there, 63.2%. We'll work with percents now. I probably shouldn't have used, because I need more room for percentages, and I need another one of these pens. Oh, this one looks good. All right, so the voltage when I'm just charging a capacitor, there's going to be the voltage across the capacitor that starts at 0, right? And then starts to increase. 63.2%, if I look at the 13.5%, that's going to give me 86.5%. So 1, 2, 3, 4, 5, 6, 7, 86.5% is right about there. And so I would keep climbing up 5%. That brings me to 95% up here. You can see how fast this is charging, dependent upon, and remember, this is 1-time constant, 2-time constants, 3-time constants. The time constant is, let's circle that too, the time constant is R times C, right? So remember how we've got it. So I'll just finish this out. So this is our charging profile of the capacitor, right? And you can see that after 5, I'm just going to, well, you could say 6, but I'm going to say after 5. Let's just go up after 5 time constants. We're down to less than 2%, aren't we? Right? We're down to less than 2%. And so you can see that this, if I was to fill this up, I'd be almost totally full. After 6, I would literally be at 99.3%. So 99.3% right there. And this is going to be 98.2%. So, we're really pretty much charged up after 5 time constants. How can we figure out what that time constant is? We know what the capacitor value is. We know what the resistor value is. That gives us our time constant. That shows us how we come up here. Now, what is this equation right here? We know that this equation is y equals e to the minus x, or as we wrote down here, v of t equals v0 e to the minus t over rc. Down here, we're going to say that v of t, and I better make a line so that everybody knows that this is referring to this equation and chart up here. This one down here, what's the equation of this? And I think everybody can sort of figure that out. Isn't it just 1 minus e to the minus t over rc? Does everybody see that? Now I'm going to derive that as well. Let me just sort of cut a section out of here. I wasn't sure which way I was going to go to the RL or see if I could do this, but I think that I might have enough room. I'm not sure. I'm going to give it the old college try to put the derivation for the charging mechanism, the 1 minus e to the t, 1 minus e to the minus t over RC in this little box here, and we'll see if that can work. That's pretty good. Okay, just a second. Hello, class. I am back, and I'm not sure if I can finish this whole derivation in this little space. I may have to flip to the next page. I don't think I've ever done that before, but I may do it this time. Anyway, let's just sort of look, and we're going to be looking at the charging phase now. So the thing that we're going to be looking at here is the green charging phase of a capacitor and why it would do that. Now, if I just looked at that charging phase where I've got the power supply that's going through the green and then charging the capacitor through the resistor, we know a couple things. We know that the current that's going through the resistor equals the current that's going through the capacitor, right? It's in series with one another, so one has to go through the other. And we also know what the current flowing through either one of those is, right? Because we can quickly look at the voltage here. In fact, I should probably draw, the circuit just by itself. Yes, I may have to use another sheet of paper, but that's okay. So if we look at this, we see that once that is closed, I just have a resistor, and then I have a capacitor in series with that resistor. And my current has to flow through both of those. So I know that this right here is going to be V sub S, V of the source, right? So we've got a DC source, that's the voltage on the source that's going to charge up the capacitor. And we're going to look at the voltage across the capacitor. And that would be V sub C. So we want to look at the voltage across the capacitor. That'd be the positive. And of course, this would be the negative because it's connected to ground. And of course, R is going to determine the current, but we know that I sub R and I sub C are the same. Now we know that the voltage over here on this side is changing with time. So we could really say that what we're looking at here is V sub C as a function of time, right? And I want to put that in there too. It's V sub C as a function of time. We know what it's going to look like. It's going to look like this. It's going to look like a 1 minus e to the minus t over RC. And in fact, I'm going to qualify this right now, and I'm going to say that V of C with respect to time is going to be equal to Vs, the source, right? Because this right here, I say V sub O, but I really mean V sub S in this diagram that I'm using here. So what is the current through the resistor? Well, we know we got V of S over here, and we know we've got V of C, whatever that is, right? Because this is going to be 0 on this side of the capacitor. And on the other side of the capacitor, it's going to be whatever V sub C is at any instant in time, right? So we know the voltage differential across that resistor. So the voltage differential across that resistor is V sub S minus V sub T as V sub C as a function of T, right? And we've got to divide that. Ohm's law, let's not forget Ohm's law, V equals IR, right? So V equals IR, Ohm's law, divided by R. So there you go. So I sub C equals V sub S minus V sub T, or V sub C, divided by the resistance in that series circuit. I think everybody can see that. All right, now let's replace a couple of the things. What is I sub C? Well, we know that the time variant form of I sub c is c dv dt, right? We used that before. And then if we take this over to the other side so that we can make this equal to 0, I'm not even sure why we have to do that though. Why don't I just take v of c over, that's the negative, I'll take that over to the other side, and I'll leave this one over here all by itself. So let's say this plus v of c over r equals v of s over r. If you don't mind, I'm going to leave the, well, okay, fine, I'll put the t there. There you go, v of c, the voltage across the capacitor at any point in time, right? Now, I think you can see what I'm going to do next. I'm going to divide both sides by c. So I get dv over dt plus v, the voltage across the capacitor at any time divided by RC equals the voltage at the source divided by RC. Does everyone see that? Okay, so I basically divided the whole thing by RC, and you know, what I can do next is I'm just going to take this and I'm going to bring it over to the other side again. I'm not even sure why I want to do that. Oh yeah, I see why didn't I leave it? I don't know. I could have anyway. Let's take that over to the other side. So I've got dv over dt equals v sub s minus v sub c at any time t divided by rc, right? Okay, now let's switch this around. Let's take this, the numerator on the right-hand side, and throw it into the denominator on the left-hand side, and throw the denominator in the left-hand side over into the numerator on the right-hand side. So I end up getting dv divided by v sub s minus v sub c times t, right? Equals dt divided by, oh wait, should I put a negative there? Well, I could do that next. Over RC. Okay, well, we've got that set up. Well, I can always switch, negatize these things in no time. So if I wanted to put a negative up there, all I would do is have to switch this around, right? So in fact, why don't I do that? I'll say that it's dv, just to follow along with your book, v sub c of t minus vs equals minus t, well, I better put dt still, dt over rc. And there you go. I've like run out of room to finish that one up there, but I'm going to go along anyway and see if I can't finish this. Let me just see. I'll tell you what. I have another sheet right back here. I hope everybody has that, but if they don't, oh, I don't even know what that is. Let me just finish this up. I think everybody can still see that, and we are going to call this RC first order response circuit. Okay, let me just continue on from where I was. And last thing that I had was D. Well, actually, yeah, why not? D. Now I'm just rewriting it 3 times. All right, dV over V of C. This gives me a little more room to minus Vs equals minus dt over RC. Now let's integrate both of those two sides. And I'm just going to go across here for a second. So this is going to, if I integrate that with respect to V, that's going to give me the natural log of V sub C of t minus Vs equals minus t over RC. Now, I think I'm missing something here. Where am I missing something? Oh, I see where I have to, since I did that integration, I'm sorry, my integral signs, let's integrate both of these. I want to give you the integral signs that we have here. This one's easy, that's just 0 to t, so yes, I am correct on that side. But this one over here is from V0, which is whatever the voltage is on there, which is usually 0, to V sub S. All right, or wait, no, V0 to, sorry about that, V sub C of t. Yeah, no, I think I already have that. V sub C minus Vs. And I have that minus Vs, yes. And then minus V sub 0. So I've got V sub 0, I've got V sub C. Okay, so I've got to punch those in there. So I've got this minus, let's just put a bracket around there, minus, so that would be V sub C minus Vs minus the natural log of V sub O minus V sub S. Whatever, in other words, what I'm saying is whatever the original voltage was on the capacitor, that's what V sub O is. V sub O equals V sub T at T equals 0, right? Okay, so I've now got this, and what I can do, since I've got those negative of one another, I can just use that identity that I had before, that the natural log of A over B equals the natural log of A minus the natural log of B. And what this gives me is the fact that, I can have that equal to the natural log of V sub C of T minus Vs divided by V sub 0 minus Vs. And that equals minus T over RC. Okay? Now let's integrate both sides. So what I get is I get V of C of T minus V sub C of T minus V sub S divided by V sub O minus V sub S equals e to the minus t over RC, right? Does everybody see that? So I want to take this off to the other side, and so I say V sub C of t minus V sub S equals V sub O minus V sub S e to the minus t over RC. Now, let's take this over to the other side. So we now find out that V sub C of t equals V sub S. And usually V sub O is equal to 0, right? Because we're charging the capacitor. So if, well, I'll put it, if V sub O equals 0 volts, then this is V sub S minus V sub S e to the minus t over RC. I think everybody can see where I'm going with this. V sub S times 1 minus e to the minus t over RC. There you go. So we have proven that it charges as 1 minus e to the minus t over RC, and we know that RC equals our time constant. And so that means that the charging is exactly opposite. Instead of it being e to the minus x, it's 1 minus e to the minus x. And of course, that brings us right back to this page too. Okay, I hope everybody got that. You can always rewind it. If you didn't, I wanted to put it back here in case somebody wanted to check or wasn't caught up. You can always go back to that other page. Thank you, and I will get on to the RL step response circuit.